I'm Caroline Ummenhofer from Woods Hole Oceanographic Institution. I'm an oceanographer and climate scientist. My work uses a variety of different tools, such as measurements of currents and temperature in the ocean, and rainfall and winds from stations all around the world. These data sets are combined, and I use them in conjunction with computer simulations of the ocean and the atmosphere to test the role of the ocean on climate. The oceans contain the majority of water on Earth, and any rainfall that falls on land ultimately has come from the ocean. So if you want to understand anything about rainfall on land, you need to look to the oceans. My work focuses on the Indian Ocean and its role for regional rainfall and extreme events such as droughts and floods. The Indian Ocean is notoriously understudied. There are only a few measurements that go back further than a few decades. Hence, we know much less about the Indian Ocean, how it works, and what role it plays in the climate system compared to, say, the Atlantic or the Pacific Oceans. In fact, the Indian Ocean has been called oceanographer's stepchild because it has been ignored for so long. This year actually marks the 20th anniversary of a new climate phenomenon that was discovered in the Indian Ocean. In September 1999, two papers came out back to back in Nature that described an unusual phenomenon in the Indian Ocean in 1997-98 that had severe consequences for the region. It's called the Indian Ocean Dipole. Now, 20 years on, we understand much more about the Indian Ocean Dipole and how it affects regional rainfall and drought patterns. We know it is a recurring phenomenon that reappears every 3 to 5 years and is associated with droughts in Australia and Indonesia and floods in East Africa, for example. There is another strong, if not stronger, Indian Ocean Dipole event happening in the Indian Ocean right now, like the 97 event. And extreme events in surrounding countries are seen again as well. The Indian Ocean Dipole has two phases, a positive phase and a negative phase. During the positive phase, anomalously strong monsoon winds off Java and Sumatra in the eastern Indian Ocean lead to cool temperatures, and in the western Indian Ocean, warm temperatures appear. Associated with these temperature changes in the Indian Ocean, wind patterns change, and cooler temperatures in the eastern Indian Ocean mean that less water is evaporating from the sea surface, and droughts result in Australia and Indonesia. On the other hand, the other side of the Indian Ocean, the warm waters of Eastern Africa, mean that there's more rainfall, more evaporation, and floods. But the Indian Ocean does not act in isolation. In the Pacific, there's a similar climate phenomenon, the well-known El Niño, La Niña cycles, that we've known for over a century. And it's often associated with failures in the Indian monsoon. In fact, it was in the 1920s that unusual conditions in the atmosphere over the eastern Pacific were put into context with monsoon failures over much of India in the late 19th century and 20th century. But it's not just humans that are affected by the Indian Ocean. Trees, for example, in the tropical rainforests across Southeast Asia experience mortality due to drought or wildfires in response to unusual conditions in the Pacific and the Indian Ocean. And Australia experiences more severe bushfire seasons during positive Indian Ocean Dipole events. In the last 20 years since the Indian Ocean Dipole was discovered, our understanding how the Indian Ocean affects regional and global climate has come a long way. This is also vitally important because the Indian Ocean is experiencing large changes. It seems to be particularly vulnerable to a warming climate, and temperatures in the Indian Ocean have risen a lot more than their counterparts in, say, the Pacific or the Atlantic Oceans. How the Indian Ocean will respond to future climate change is an active area of research that the oceanographic and climate science community is working on right now.